Before Newton told us what force does, he told us what happens without it. And the answer changed physics forever. This is episode 1, Newton's first law of motion. We will understand the law from the ground up, apply it to real different system. A missile's fire, the rocket engine burns for exactly 3 seconds. Then it shuts off completely. Does the missile stop? No. Does it immediately slows down? No. What actually happens? It keeps going. Same speed, same direction. This feels wrong, I know, because on Earth things stop when you stop pushing them. But that's because of friction, air resistance, not because of some natural law of universe. Remove those forces and the object moves forever. This is Newton's first law. And then prove it visually with Python. Let's go. Here is the formal statement of the law. An object at rest stays at rest, an object in motion stays in motion at the same speed and in the same direction, unless acted upon by external unbalanced force. Two parts of this. Part 1, things don't move on their own. A book on a table stays exactly where it is. Nobody needs to hold it there. It resists starting. In part 2, things don't stop on their own. Once something is moving, it keeps moving at the same speed, same direction forever, unless something acts on it. The only thing that changes either state is net external unbalanced force. The word unbalanced, we will make it precise in a moment. Newton's first law has another name, the law of inertia. Inertia is a tendency of an object to resist and change in its state of motion. Three things you need to know about it. First, inertia depends entirely on mass. More mass means more inertia. A 70-ton tank resists changes like start, stop, or turn. A 70-gram bullet has almost no inertia at all. Same law, completely different scales. 2. Inertia resists change in direction, not just speed. When a missile changes course mid-flight, a force must act on it continuously. It flies straight again, even turns require effort. That effort is fighting inertia. 3. Inertia is not a force. This is something students often mix up. Inertia is a property of a matter like mass and like density. It tells you how much an object resists being accelerated. It doesn't push or pull anything, it simply resists. Let me make the word unbalanced precise because it matters enormously. Balance force, net force right now equals to 0. The object doesn't accelerate, it either stays still or continuously moving at a constant velocity. No changes happens. Whereas unbalanced force, net force is not 0. Motion changes, the object speeds up, slows down, or changes its direction. Newton's first law is overdriven by whatever the net force is acting. Real example is a fighter jet is cruising at a constant altitude, constant speed. Thrust equals drag. Lift equals weight. All forces are balanced. Net force right now is 0, constant velocity. First law holding is perfectly over here. Pilot fires the afterburn. Thrust now exceed drag. Force unbalanced. Net force forward. Jet accelerates. That single moment, that transition is the line between this episode and the next episode. Here is the most beautiful real world proof of Newton's first law in existence. Voyager 1. Launched in 1977, nearly 50 years ago. Its engine have been off for decades. It is currently 24 billion kilometers from Earth and it is still moving at 17 kilometers per second. Nobody is pushing it, no engine, no fuel, no thrust. Why? Deep space is nearly perfect vacuum. No air, no drag, and there is no friction. Nothing to resist the motion. At the distance, gravity from any planet is effectively negligible. Net force is 0. And Newton say when net force is 0, velocity stays constant. 17 km per second, same direction, same speed, no fuel required. Just the law. One spacecraft has been running this experiment for nearly 50 years and it keeps proving Newton's right every single day. Now, second application, closer to the ground. A military armored vehicle which is moving at 80 km per hour, the driver brakes suddenly. The vehicle decelerates. The brake applied force to it. Fine. Okay. What happened to the soldiers inside? Their body were moving at 80 km per hour. No force has acted on their bodies yet. Newton's first law, no net force, no change in motion. Their body continuously forward at 80 km per hour until something is stopping them. A seatbelt, a wall, the flow, that contact, that is the force that is stopping them. That sudden impact is what causes the injury. This is exactly why military vehicles have restraint system. This is why sudden stop in combat situations are so dangerous. Newton wrote this law in 1687. Engineers has been using it to keep people alive ever since. Six completely different worlds, but one law. Voyager 1 engine of for 40 years is still moving at 17 kilometers per second. Net force is zero. Soldier in a vehicle, body keeps moving when the vehicle brakes. Inertia. Cricket ball in the air, once it leaves the bat, the batsman is no longer involved. Gravity and drag now acts. Missiles after engine burnout. Momentum carries it, no thrust required. Hockey puck on ice, nearly frictionless surface. When pushed, slides indefinitely. Satellites in the orbit, moves at constant tangential speed. Gravity curves the path, but doesn't slow it down. One law, once you say it, you cannot unsay it. Before we move to the Python, I want to clear up the most common wrong belief about motion. The mistake, a moving object needs a continuous force to keep moving. This feels like a common sense. It sounds reasonable. One of the greatest minds in our history, Aristotle also believed it. But it is wrong. The correct statement, a moving object needs a force only to change its motion, not to maintain it. Why does the wrong statement feels right? Because on Earth, friction is there. You push a book, it slows down and stops. You assume the stopping is natural, but friction is a force. Okay, the external unbalanced force. Newton was describing it. Friction is the doing the stopping, not the absence of your push. Okay, remove the friction, remove the air resistance. A single push would make that book move forever. You know about the Voyager one. One push in 1977, still moving forward. This is the proof. Now we prove it with Python. The theory is clear now. Let's make it visualize. We will build two graphs side by side. On the left side, an object with zero net force. Newton's prediction, constant velocity, a straight line on the position time graph we will get. And on the velocity time graph, a flat line, which is unchanging. On the right side, an object with a constant force acting on it. Velocity increases, position curves upward. The visual difference between these two graphs is Newton's first law. You will see it in about 30 lines of Python code, and once you've seen it, you will never forget it. Two library, same two in every episode we are going to use in this series. First will be NumPy. How we are going to import it? We are going to use import NumPy as NP. NumPy handles sparse numerical calculations because it uses arrays. np.linspace will generate 500 times value evenly spaced in between the 0 to 10 seconds. Means it will increase the number of the points over here in between the 0 and 10 seconds. We then plug each into our physics equation and to get the position and the velocity at every point over here. Then after that, to visualize it, we are going to use matplotlib. We are going to use this import. How we are going to import it? Which is going to use import matplot.pyploy as plt. Okay. Python standard, basically Python library. Other is Cmon, but right now we are going to use what? Matplotlib over here, and the subplot is over here, plt.subplots. With one row and two columns gives us two side-by-side graph on one figure. Means you can install it using pip install numpy, matplotlib. You can install both of the libraries over here. Here is a complete code. Let me walk through every part of it. Start with import numpy and matplotlib. Then the parameters will be using the variable t equals to np dot linspace 0 to 10, which is basically 0 second to 10 seconds. And it's going to divide into the 500 points in 500 times points in between the 0 to 10. And after that, the initial velocity, which is given by 5 meter per second. And after that, the acceleration for the force case we are going to use over here, which is what? 2 meter per second. Now, case one, no, if you are applying no force over here, this is Newton's first law being plotted over here. Okay, so the variable, there are two variables are there. First is x underscore known underscore force, which is equals to v naught multiplied by t over here, which is going to give the straight line. And secondly will be the v underscore no underscore force equals to np dot full underscore like. So over here, what it's going to give us velocity is the same value everywhere, which is basically showing the flat line using it. So x equals v naught times t, which is linear constant velocity. This is Newton's first law. In the case 2, with a constant force, these are the kinematics equations. Basically, as you can see over here, we are going to use these kinematics equations, which is x equals to v naught t plus half a t square, which is going to give the curved line. And secondly, the v equals to v naught plus at, which is basically going to give the rising line over here. These are the kinematic equation as I told you earlier, which we will derive properly in the episode number 4. For now, notice the curve and the rising velocity over here. Force is acting as it is, the force is acting. That's why we are seeing this kind of curve over here. Then the plot, two graphs side by side, as you can see. Okay, green for the no force, orange for with force on the both the graph. Titles, labels, title layout, then show, we are going to show it, run it, and then compare appears results. Okay, here is the Python output, two graphs side by side. Left graph, position versus time, green line, no force, perfectly straight, position increases at a constant rate. Okay, orange line with force, the curve bends upward as the object accelerates over here. Right graph, velocity versus time, orange line, velocity rises steadily, a force is acting, constant acceleration is over here. Now look at the green line on the right of the graph, flat, completely flat, as you can see over here. This is constant velocity. This represent what? Constant velocity. That flat line is the Newton's first law. No force, no change in velocity. That is being proven graphically using Python. Python didn't simulate the physics, okay? It is making, make Newton's idea viable over here. Visualization. Now, pause the video right now, and we can say that a 2 kg hockey puck moves a 2 kg hockey puck moves across a frictionless surface at 6 meter per second. A player pushes it in the same direction with 4 newtons of force for 5 seconds. Part A, what is the puck's speed after 5 seconds? Part B, what if the player never pushes it at all? Okay, think about it. Part A need two steps and two formulas, and part B needs nothing, just the law itself. Now, ready for the check? Okay. Part A, with the force applied, step 1, find the acceleration of force F divided by m, which is equals to 4 divided by 2, and we will get the acceleration value over here. So the final velocity, using the final velocity formula over here, we will get what? 16 meter per second. Okay, what are the key takeaways from this? 3 things. Carry this out on the video. First, object resists change. As we know that object resistance, not motion itself. A moving object does not need force to keep moving. It needs force to start, stop, and to turn. That's all. Second, friction is a force. Okay, it's not a natural cause which is being applied on the object, not a default force, as you know. Things stop on Earth because friction acts on it, not because stopping is natural. In vacuum, as we can see, if we push any object in the space, it will continuously moving. Okay. And the third, zero net force means constant velocity. These are the three ideas, are the foundation for every episode that we are going to follow. Next episode, Newton's second law, which is F equals to ma. If you find this episode interesting and it is worth for 13 or 15 minutes of your time, subscribe for more. Meet in the next video. Bye bye.